I'm Saki He, and this time I'm going to talk a little bit about my thoughts toward this problem and introduce some of the features and grid algorithms in this problem. Okay, first, I want to show you our questions. We add an attribute which is the cost to each edge. We want to keep maximum flow as the least desired value k, while make the total cost as small as possible. We pay all the costs for one edge as we are using this edge, no matter how much we use it.
Hello everyone, this is Jen King, and first I'll talk about why this topic is important to me. So the question we're trying to address is very interesting and useful because essentially we're taking into account multiple properties for max flow problem. For example, we wasn't considering the cost of building the pipe when we address the traditional max flow problem for pipe system. In our cases, we give each pass two properties, one cell capacity, another one could be time cost. Our problem can be applied to famous warfare in European history, and it is a battle of Normandy. Americans are trying to send 10,000 soldiers onto the beach using different sizes of boats. And different routes, and there are routes between each battleship to transport soldiers, and each battleship has different size of boats. The optimal solution is to send the soldiers onto the beach as fast as possible using as few boats as possible. However, there are cases when boats with large capacity it's sank by the enemies. Like what should the general do? How can they send the rest of the soldiers onto the beach as fast as possible without many lost boats?
In large networks, there are often multiple valid routes to the same destination. The optimal route, calculated by algorithms, will always forward the traffic through the optimal path. This feature often causes the following two problems. First, all traffic is transmitted through the optimal path, which can easily lead to load imbalance. Second, if the optimal route in the network is faulty, traffic is still transmitted along the optimal path, resulting in traffic loss. When we know the cost and the complexity of all links, it's a very wise choice to implement traffic transmitting along different physical links. Therefore, the multi-path routing problem is worth our research. It can yield a variety of benefits, such as fault tolerance, increased bandwidth, and improved security.
Most healthcare systems rely on a robust and complicated supply and demand network. That supply, that I and many others rely on, is maintained by a hospital network at a considerable economic cost. For example, the ability for a blood donation to be quickly and affordably transported from a source to a destination has really been crucial for me my entire life. Therefore, I am motivated in this project to investigate the kinds of deliveries that can be executed at the smallest cost.
This problem is especially useful when we are analyzing a flow problem, such as if you want to rent the pipes of a sewage treatment plant and they offers you their pipes which you have to pay all the cost if you are using the pipe, or another circumstances, so that this is a little bit different from minimum cost or minimum flow or maximum flow or minimum cost problem, and that's what we want to get it and how we solve this problem. First of all, the problem seems to be a non-NP problem actually, but if we add one piece of constraint, it will be an NP complete problem. We will show in our report, and I will talk a little about it. As you can see, this is a graph, and I will we will reduce independent set problem to this problem with one more constraint. So here is the independent set problem. On the left side, there is a graph of the used or saturated problem. That means there is the flow graph, and when every time you want to use an edge in it, you have to use all of the capacity, and this is be proved to be a NP hard or NP complete problem. As briefly talk about this, we have two set of vertices. One set is the V, one set is the edges, whether it exists or not. As you can see, we have vertices 1, 2, 3, 1, 2, 3, and we have these edges. These are the second set. Have a source connected to each of the vertices, and with the capacity of number of vertices is v minus 1 capacity to these 3 edges, and k is the value of independent set, the largest independent set size. So if we have a largest independent set size of this size, we can have a maximum flow while satisfying the not used or saturated constraint. The maximum flow value is v minus 1 multiplies k, and it's pretty obvious. There's another point. The edges are connected to the sink by these rules, so that if the edge does exist, it will have only one capacity. If the edge does not exist, it will have 2 capacity. So we built this graph and connected the vertices to all the edges it connected, like vertices 1 is connected to 1, 2 edges and 1, 3 edges. So as you can see, this graph is pretty obvious because we have labeled all the edges used as black and all the edges not used as blue. So you can see the S2 and S3, they are 4, and they go with 2 to 1 2, 2 to 2 3, 3 to 2 3, 3 to 1 3. These 4 edges are the medium, and these 3 edges 1 to 1 have a flow of capacity 4. This is exactly what we expected, and then we will show. I will show you that when we increase one node into it, it will still keep these attributes. As you can see, if we add another node vertex 4 into this independent set graph, we will have where we have the largest independent set k equals 3, which is 2, 3, 4, these 3 nodes, and we build this graph a little bit, expand this graph like this. Because 4 is connected to 1, the 1 has only 1 edge, which means 1 capacity edges towards the sink. And as you can see, this graph we could do with k equals 3, but for the right side we cannot do this because when we are increasing the capacity of each of the S2, S3, there is one more capacity which we have to occupy due to the not used or saturated constraint. So we have one more edges out from this towards 2 and 4, 3 and 4. So we must satisfy this node must have edge of capacity 2 towards the sink. So they can't be connected to, like 2, 4 is must not be connected to 3, 4 must not be connected. If it is connected, then you can see this independent graph has only k equals 2, not 3, and this will not reach 3 multiplied 3, but 2 square. Graph shows on the right side. These two graphs are identical problems. Even if we have the not used or saturated solution is NP, we have also need exponential times to reach our final result, because there are the combination of each of the flows are exponential size, and there might be exponential size of the flows which satisfies the k minimum flow constraint. So if you want to look for each edges and look for the if there is a flow to have something like that, that means I have the flow which cost is minimum. Look into each one and calculate the cost and choose the smallest one. It still costs exponential time. So we add a constraint that our graph is designed well, and we only have a polynomial set of flow that satisfies this capacity of k. So we can look into each of the flow and determine which is the smallest, and therefore we reduce this problem to our original problem, but one more constraint. So here's a small pic of the code here. The greedy algorithm is pretty straightforward. When we are choosing argument paths to form our flow graph, we choose from the residual graph. We just choose the one which gives us the maximum value. I mean, if the cost is low and capacity is large, then we want this pipe, or say the cost is like a path cost. The cost adding all the pipes during the path, and that's over the capacity, the minimum capacity in the set, because that's what we can get from this path. This is pretty straightforward. As we add in these passes, once we reach the capacity of K, we desired capacity, we will just stop, and the cost may not be optimal, as you can see easily, but this solution will result in a polynomial time, not exponential time. If you want to get an exponential time algorithm that is more than NP problem, I'm afraid you have to have an exponential or more time complexity one. So this algorithm is still useful.
It's pretty simple. So the cycle canceling algorithm takes an iterative approach. Start with any valid flow with the desired magnitude. It then iteratively reduces the cost by moving the flow to cheaper edges without violating constraints. So having the max flow constant. So the first thing we need to do is to calculate the max flow and get the final residual graph. While we iterate through it, possible ways to redirect the flow can be found by evaluating the residual graph of the flow. So sending flow along a cycle in the residual graph always leads to another valid flow and keeps the total flow constant. If the sum of the cost for the edges in the cycle is negative, changing the flow will reduce overall cost and improve the solution. And negative cycles can be found by running the Bellman-Ford algorithm. And after we identify a cycle, some amount of flow can be sent along all its edges until the one with the lowest capacity saturates. This will remove the edge from the residual graph. Since the new residual graph might still contain other cycles, the algorithm has to iterate and run the Bellman-Ford algorithm again.
When analyzing this algorithm, one of the most important factors was determining how many iterations of the modified Bellman-Ford were needed. The cost associated with each edge in the graph and the residual graph must be integers, and as a result, each iteration of our modified Bellman-Ford algorithm reduces the total cost associated with our flow by at least 1 each time. In every iteration of this algorithm, a negative cost cycle is found in order VE runtime. Our cycle canceling algorithm will have a total runtime of order VE times the absolute value of the cost of an edge times K. There also exists a general bound of the cost of an edge times K greater than or equal to negative E times the maximum edge cost times the maximum edge capacity. This means that the runtime in total will be order VE squared times the maximum edge cost times the maximum edge capacity. Through all of our analysis, we have determined that our problem is NP hard. This occurs when flow is greater than K, and K is a determined combination of edges where the graph is balanced. We can find an answer using our solution greedy.java program by finding an augmenting path in our graph which has the smallest minimum cost to capacity value in each iteration. If we consider edge cost as cost per unit of flow rather than cost of entire edge, we can solve our problem in order VE squared times maximum edge cost times maximum edge capacity through the use of our cycle canceling algorithm.